Hello viewers, welcome to video number 113 of the channel MALACHEMPHILIC, and this is the 53rd episode of Chemical Thermodynamics where the topic is chemical potential. So let's start. In my last video, I have discussed about this partial molar property where I told that for an open system, any extensive property, say X may be internal energy, it may be enthalpy, it may be Gibbs free energy, whatever it is not only the function of temperature and pressure, but also it is the function of number of moles of different component present in the mixture. So, if X is an extensive property, then we have seen that this dole X by dole Ni at constant temperature, pressure and all other composition of the all other components, say N2 and all these things, say Nj and J naught is equal to I. This is the partial molar property. Which property? Here it is X, okay, and it is denoted by Xi bar, partial molar property of ith component. This we told. Okay. Now this chemical potential is the partial molar Gibbs free energy. Then what will be its expression? Chemical potential of the ith component will be dole G by dole Ni at constant temperature, pressure, say N1, N2, N, say Nj, J naught is equal to I. Here it is N1 also. Okay. So, this is the chemical potential of the ith component. Then, how can I define this chemical potential? So, we can write that the chemical potential of the ith component, right, the chemical potential of the ith component is the increase in free energy, means Gibbs free energy, increase in free energy per mole of the component, here it is I, component I, when small amount that is dNi, the small amount of the component, which component? Ith component is added to the system, say system is a mixture of ideal gas or whatever it is, added to the system at constant temperature, pressure and composition of other components, right? So it is nothing but the change of this Gibbs free energy with respect to the change of number of moles of, or change of the moles of any component, okay, at constant temperature, pressure and the composition of the other component, right? So this is your chemical potential. Now, just like earlier one, we can write this extensive property gives free energy. G is the function of temperature, pressure, N1, N2, Nj. It is open system, so it is not only the function of temperature, pressure, but also the number of moles of the components, right? So from here we can write dG is equal to dol G dol T at constant pressure and the composition of all other components. Say I am considering N1 plus N2 plus Nj, that is equal to N, total composition, total number of moles, dt, plus we can write dol G by dol P at constant temperature and all the composition, constant composition of the components, dP, plus we can write dol G dol N1, then temperature, pressure, say N2 plus say Nj. Here J naught is equal to 1 dN1 plus say dol G dol Ni, temperature, pressure, then say N1 Nj, and J naught is equal to I dNi. We can write now at constant temperature and pressure. That means this part will not be there, this part will not be there. Then what we can write? dG is equal to, we can write dol G dol N1, then temperature, pressure, then N2 and all other components, say Nj up to J, then dN1, here J naught is equal to 1 plus say it is dol G by dol Ni at constant temperature, pressure, N1 Nj, J naught is equal to I dNi. Okay, can write now if the system has, now before that, see, already I told you that dol G dol N1 or this partial molar free energy, that is the chemical potential. So what I can write? dG is equal to mu1 dN1 plus say mu2 dN2, like that, plus say mu I dNi plus mu j dNj, we can write, right? Now when the system has definite composition, that is N1, N2, Nj are the number of moles of 1, 2 up to jth component. Then on integration, this is equation number 1. Then what we can write? On integration of 1, on integration of equation 1, what we can write? G is equal to N1 mu1 plus N2 mu2, say like this, plus Ni mu I plus Nj mu j, right? So this is very important equation. G is equal to N1 mu1 plus N2 mu2. This you should remember. Now, when it is a pure substance, that means only one component is there. So, for pure substance, only one component will be there. Pure substance, say one pure ideal gas, then what it will be? G will be is equal to, say, n is the number of moles and mu. Okay. When n is equal to 1, that means for 1 mole of pure substance, 1 mole of pure substance, then what you can write? G is equal to mu. This is also important. Okay. G is equal to mu. Right. Now, see this chemical potential of a component in the mixture of ideal gas, in the mixture of ideal gas, we can write mu I, the ith component, mu I is equal to mu I 0, say here I am writing in terms of partial pressure, plus RT ln Pi. So, Pi partial pressure of the component, partial pressure of the component. Right? Similarly, we can write mu I C. C is the molar concentration, is equal to mu I 0 C molar concentration plus RT ln Ci, where Ci molar concentration. Okay, or we can write mu I x, x is the mole fraction, is equal to mu I 0 x plus RT ln xi. Okay, so xi is the mole fraction. Right? Now we'll take any one equation. Say if I take this equation, say mu I C is equal to molar concentration here, mu I 0 C plus RT ln Ci. Okay, and when Ci is equal to 1 mole, then what we can write? Mu I C is equal to mu I 0 C. Right? This mu I 0, this is known as the, say, mu I 0 means ith component, mu I 0, this is known as the standard chemical potential of, say here it is ith component. Okay. Now, for pure substance, already I have shown you that for pure substance and 1 mole, G is equal to mu. Already I have shown you. So, now, this is for pure substance, this one, for 1 mole. Okay. Now, this G0 standard free energy will be is equal to standard chemical potential of the pure substance 1 mole at the standard condition. Standard condition means pressure is 1 atmosphere and temperature is mostly we take 25 degrees centigrade, that is 298 Kelvin. Okay, so this one we know. So like this, what we can write, that standard chemical potential, okay, standard chemical potential of the pure substance is the free energy or molar free energy at the standard state, right? So standard chemical potential of the pure substance, a pure ideal gas, pure substance is the molar free energy at the standard state, that is pressure is equal to 1 atmosphere and temperature is equal to 298 Kelvin. Okay, so G is equal to me already we have proved for 1 mole. When it is in the standard state, then it is standard chemical potential, and standard chemical potential is equal to standard free energy. That means the standard chemical potential of the pure ideal gas is the molar free energy at the standard state. Okay. Now we'll define what is the standard free energy change. This is a standard free energy change, delta G0, free energy change. How can you define? Standard free energy change will be the change in the free energy when 1 mole of the substance is produced from the constituent element at standard state. So here this is change in free energy, when 1 mole of the substance, formed from the constituent element at the standard state. Standard state means P is equal to 1 atmosphere and T is equal to 298 Kelvin. Okay. Now we'll define one more thing, that is, okay, this is one problem. We'll do it after finishing. So now standard free energy change of the reaction, we define it as standard free energy change of the formation of, this is formation of product, minus standard free energy change of the formation of reactant. Or this can be determined or calculated this way also. Standard free energy change of the reaction is equal to standard enthalpy change for the reaction minus T standard entropy change of the reaction. Okay. Any two way you can calculate this standard free energy change of the reaction. Remember, the standard free energy change delta G0 is more important than free energy delta G. Okay, and now one more point, the standard free energy change of the pure substance, okay, of the pure substance, obviously it is pure substance because standard means we are taking 1 mole of the pure substance at the naturally occurring state is equal to 0. This you have to remember. Standard free energy change of the substance at the naturally occurring state. That means free energy change when during the formation at the naturally occurring state, that is equal to 0. Therefore, what we can write? See, delta G0 of oxygen in the gaseous state is equal to 0. Similarly, delta G0 of hydrogen in the gaseous state is equal to 0 because hydrogen and oxygen in the nature they remains as gas, right? But delta G0 of bromine in the gaseous state is not is equal to 0 because bromine exists in the liquid state. So, delta G0 bromine in the liquid state, that is equal to 0. Similarly, delta G0 of iodine in the gaseous state, it is not is equal to 0. It is not naturally occurring. In nature, it exists as solid. So, delta G0 of iodine in the solid state, that is equal to 0. So, this point you try to remember. Okay, very important. Now, we'll solve this problem. So, the problem is this iodine gas plus iodine solid plus hydrogen sulfide gas gives the product hydrogen iodide 2 moles and sulfur. Okay, we have to find out the delta G0 of the reaction. We know that delta G0 reaction, just now we have seen, that is equal to product. That means that delta G0 of formation of HI, right, minus delta G0 of formation of reactant, that is H2S. Why you are not considering this and this? Because iodine, that is the element. Okay, pure substance, sorry, here one thing I forgot to tell you. Pure substance, no, it is 1 mole of the pure substance in the elemental state, or we can write delta G0 of the element. Sorry, here we can make it delta G0 of the element. This we have to rectify. T0 of the element, standard free energy change of the element at the naturally occurring state is 0. So, here it is, iodine is element and it is in the solid state in the naturally, that is the naturally occurring state. So, this is 0 free energy change or standard free energy change. Similarly, sulfur is element and naturally occurring state is solid. So, delta G0 of sulfur is 0. So, we have to consider this product and this reactant. Right. Now, so delta G0 formation of HI, they have given 1.8. Here are 2 moles are forming. So, 2 into 1.8 minus formation of the reactant is 30 kilojoules per mole. So it is 3.6 minus 30, minus 3 means 27, that is 26.4 minus 26.4 kilojoules. Okay. So as it is negative, since delta G0 is negative, therefore reaction is spontaneous. Hope you have understood. Thank you.